Good morning, good evening, and good afternoon. Thank you for joining us. My name is Dawn Cullum, and I am the Senior Events and Training Coordinator for Cetera University. As regulators and sponsors, Cetera recognizes the growing importance of model-informed drug development. We are committed to educating the next generation of experts in this field by partnering with eminent scientists and at designated academic centers of excellence around the world. This year, our Express webinar series will be conducted by our partners and centers of excellence. Today, Dr. Cardot will be kicking off our series by discussing dissolution modulization, troubleshooting, and use. Dr. Cardot, I now turn it over to you.
Thank you, Dawn. So I hope that the sound is clear. It's okay?
It is.
So I can start. So welcome anybody. I am very pleased to be the first one to make the first webinar about the dissolution modulization and troubleshooting and use, knowing that within this webinar, we are going to discuss about the dissolution, but also about how the model of the dissolution can be used later on for example, modeling the absorption and or to construct IV-IVC. During this presentation, we are going to see many things. First of all, what is dissolution? The second thing, what is in vivo absorption curve, how we can modelize them. Then the classical problems that we can have and the use in IV-IVC, either for the long-acting injectable formulation, which are going to be given as example, or also, for example, to fix dissolution limits. Then we are going to give conclusion, and you have a list of references, and among them, two which are very extensively used in this presentation, which were made by Ivan Atomic in 2016 and 18. So the first thing that we are going to see together is what is dissolution. We have to know that the dissolution is something which is used in a lot of places during the registration of a drug and later on when you want to release batches. That means we are going to use dissolution in the production when we release batches, but that also is going to be used during the submission of the report and during all the variations that you can have. Then we can use also the dissolution to support biowaivers. Biowaivers which can be used for a regulatory approach, that means to submit a dossier, but also that we can use, for example, during the sourcing of API and other formulation. And we can use the dissolution from the formulation and to the in vivo performance in the development and optimization of the formulation. And then again, we can use in vivo performance and production when we are going to use IV-IVC, either to optimize the formulation and or to predict the in vivo performance. In all those cases, we are going to use dissolution and dissolution curves. To simplify, the dissolution is something which is going to be here on the right side of this slide. The dissolution depends on the apparatus, media, and parameters of the dissolution system, of course. And what is going to reflect? Is going to reflect the formulation and also the process of manufacturing. By formulation, it's obvious that a modified release, an immediate release formulation, are not going to have the same dissolution pattern. But within immediate release, you can see differences. Within modified release, for example, slow release, you can see differences. Those differences can be linked either with the formula, that means the type of excipients that you are going to be used and the proportion of various excipients, but also about the parameters of the process. That means how you are going to create, for example, the granulate, and later on, how you can make the tableting, coating of those granulate. That is also valid, of course, when you have other type of formulation like implant, like depot injectable formulation, and so on. Then also something which we are going to see in dissolution is going to be the nature and the quality of API. Quality of API means the quality itself, but also all the parameters of importance, like, for example, the particle size, the crystal shape, or the various polymorphs. So what we are going to measure? We are going to measure at the end the portion dissolved of the API versus time. That means that is going to represent what was released from the formulation and then what was dissolved to form a solution. So we have already here 2 or 3 things which are going to be concomitant. The first one is the fact that we are going to release and then to dissolve. That means you can, for a tablet, you can first disintegrate the tablet. But the disintegration do not mean that you are going to release the API, neither you dissolve it. That means only that you go back to the granulate. But then you need to have a release from the granulate and a dissolution of the API. That can be very fast or that can be slow. For example, when you have a slow disintegration, you may have, of course, a slow dissolution. But when you have a fast disintegration, that do not mean that you are going to have a fast dissolution. That depends of the nature when you have a granulate of a granulate. So what we have at the end is nothing more than this type of dissolution curve. We have a % dissolved versus time. That is very nice. You have a lot of data points here. But very often you may miss one time point which could be of importance when you want to predict something. When you don't have it, one way to have it later on or to simulate it is to use a model. The most simple one, for example, between these 2 time points here is to make a linear interpolation. But that means that you can over or underestimate the value. So another way to proceed might be to make a modelization of your plasma concentrations, of your dissolution curve, excuse me. So why we are going to do it? We are going to do it because somehow we are going to have the development of a formulation and then of a dissolution test. And this dissolution test is going to be better if you can use it to predict the in vivo behavior of your formulation. When you can use the in vitro test to predict the in vivo behavior, you have a very powerful tool and you can use it very easily for biowaivers and, for example, for IV-IVC. So that means somehow that we have here 2 types of dissolution tests. The dissolution test that you may use in development and the dissolution test that you want to use in QC. For the development one, you do not care about the number of samples. You do not care if your dissolution is going to last for hours or days, for example, for implant. In QC, you want to try to have something which is going to be very robust, which is going to be standardized, and if possible, which is going to be rapid. If you want to have something which is going to be optimized, you may have the same dissolution test between the development and the QC. And if that is the case, that do mean that you have a very strong evidence at the end that you can predict everything based on the dissolution. So what do we have? We have also dissolution somewhere else. We have dissolution not only in vitro, but also in vivo. I put dissolution in quotes here only because it's something which may be strange when we start to discuss about plasma concentration, to say that we have one step which corresponds to the dissolution. To simplify it, when you have here the plasma concentration are here in the middle of the screen. When you have the plasma concentration here, what we can see is those plasma concentration are going to depend on something which is here in green and then here in red. First of all, you need to release the drug from the drug dosage form and to dissolve the API. When you have released the API and dissolved the API, you have formed a solution. And only this solution can be absorbed and go through the membrane. When it's a tablet, you may have a first pass effect before the blood. But for example, when it's an implant under the skin, you may not have this first pass effect. But everything is going to be governed by the time needed to release the API and then to dissolve it. If you take that into consideration, what is quite important to understand is that the 2 parts here, which are in green, correspond to nothing more than the in vivo dissolution of the API. When the drug is dissolved, it can be absorbed. What is going to limit the blood concentration is going to be either the release of the drug from the drug dosage form, or the dissolution of the API, or the permeation or absorption. When you have a slow release formulation, you make this formulation in such a way that the release and dissolution of the API are going to be the limiting factor. If that is the case, that means you can study it in vitro. But also you can use the same in vitro tool to modelize, in this case, the absorption. So to simplify, what do we have? We have the dose here, which is the D. Then you have the VD, which is nothing more than the blood, and that is a very simple model. And you have the input of the drug in the blood, which is going to be here, for example, represented by the key A. Key E represents the elimination. So the key A, which is here, is going to be limited either by the in vivo release, the in vivo dissolution, or the in vivo absorption. One is going to be limited by the in vivo release and in vivo dissolution. We can think in this case that we are able to make an IV-IVC because the limiting factor that we have in vivo and in vitro is going to be the same. It's going to be the performance of the formulation. If that is the case, that means you can use the same tool between in vitro and in vivo. So that is exactly what I said in this slide. The in vivo input is going to be limited either by the dissolution or the permeation. And for slow release formulation, you think that is going to be by the dissolution. So if I start something like this, that do mean that I have something which is quite easy. If I have the same limiting factor between in vitro and in vivo, I can try to connect them, and that is called the in vitro in vivo correlation. Don't be afraid, we are going back very soon to all the troubleshooting in vitro dissolution modelization, and you will see in vivo absorption modelization. IV-IVC is nothing more than a link between in vitro and in vivo data. And when we have exactly the same type of phenomena between in vitro and in vivo and the same limiting factor, that do mean that in practice we can make a level C IV-IVC. So what we can do, I can do here nothing more than a modelization of a dissolution and absorption curve. And if I have the same model for the dissolution and absorption curve, in this case, I'm sure that I will have a very successful IV-IVC. So now we are going to start the dissolution modelization. The dissolution data are as the in vivo data. They could be modelized. The advantage is to make a right model of the in vitro data is that you can generate any missing point if needed. That could help you in this case really to make something very easy, which is going to be to generate missing sample and to have a very simple way to make time scaling. So the only thing is that you need to have enough data to generate the right equation. So you have two major classes of model. You have a mechanistic model like the Iguchi, Cross-Meyer-Pepas, Hickson-Crowell. That is only some of them that I cite here. You have a lot of them. You have empirical models. You have Hill, Weibull, McCoy-Banachar, a lot of other type of models, including very simple one like simple exponential or linear function. The important thing that we must keep in mind is that those two models do not highlight the same thing. The mechanistic model of in vitro dissolution tries to describe a mechanisms of release. For example, if you have an Iguchi, is going to be a diffusion through a matrix. If you have a Hickson-Crowell, it's more a dissolution of a pure API in form of spheres. So what is very important to understand is that those mechanistic models underline mechanisms of release. That is nice, but that is not always the case. First of all, that means you do not know always what is going to be the real mechanisms. And the second thing, which is quite important, is that you can have more than one mechanisms for the same formulation over time. You can start by a diffusion and you can finish by an erosion. That means in this case, a simple Iguchi model cannot work for all the phases. The empirical model, it's more the Phoenix approach. What is quite important to understand here is that you do not need to know the release behavior. That means you need to have the release curve, but you do not know to know what is the behavior. That means if it's more a diffusion or an erosion. You are only going to describe the curve through some parameters. Very often you have two main parameters. The first one is the slope and the second one is the time factor. In the model proposed by Phoenix, two of them are based on time factors, which is in this case the mean dissolution time. And those two models are the Hill and Weibull models. What is quite important to understand when you have a time factor like a MDT is that it's very simple later on to make any time scaling. Either you're using the inverse of the release function, which was treated in a past webinar, or using something else, which is a direct comparison of the functions. But you may have problems. And one of the problems is, first of all, when the dissolution is not reaching 100%, or when you do not have enough sampling point. When the dissolution is not reaching 100%, the risk is that you cannot describe everything. And if you have attended one of the past webinars about the absorption, something which was quite important to understand is that it's the same thing for the absorption. You must always discuss the absorption as a fraction of the dose which could reach the systemic blood flow, and not as a fraction of the dose which reach really not at the dose which reach really the systemic blood flow. That means, like in a Wagner-Nelson equation, you must reach 100%. So which are the empirical models? Don't be so afraid by the formula that you have here in the top left part of this slide. You have 4 equations which are described in the modeling least square methods dissolution models. Those equations are the Hill equation, the Weibull equation, and something which is combination of 2 Weibull, which is the double Weibull. The advantages of a double Weibull is that you can describe something with, for example, with 2 absorptions, which could be the case, for example, when you have an initial one for tablets and then, for example, an enterohepatic recycling. You have McCoy-Banachar, which is a model which is based on the fact that you are going to describe something before and something after the Tmax, and somehow you imagine that after the Tmax you have something which corresponds to the maximum of the quantity absorbed. You have here in the bottom of this slide all the symbols which were used. Something which is quite important to understand also is that you have a number of parameters to be estimated. For example, for the Hill and Weibull equations, you have the F infinity, the B, which is the slope model, and the MDT, which is the time factor. For the double Weibull, you have F1 and F2, which is 1 minus F1 if you prefer, then MDT1, B1, MDT2, B2. So you have here also factors. So that means when you have here, you have 3 factors for the Hill and Weibulls, and for the double Weibulls, you have 4, 5, or 6. We can discuss about that. In all those models, you can also add a lag time if needed. Why Hill and Weibull equations are very often used? They are very often used because they are extremely flexible. For example, here, which is the Weibull equations, you have the F infinity, which corresponds to the maximum quantity which was dissolved and or absorbed. You have the MDT, which is the mean dissolution time, and B, which is the slope factor. What is quite interesting to see is that the slope or shape factor can describe a lot of things. If your B is below or equal to 1, you are here on the blue and yellow curve. That means you are more in exponential function. When the B is really greater than 1, which can be either a little bit the yellow, but more here the purple and the black one, you can see we are almost sigmoids. That means with these simple equations, you can describe everything for an exponential function to a sigmoid function. So that means it's quite interesting to see that. When you have double Weibull, is nothing more than using 2 Weibull equations, one after the other, or starting both of them at the same initial time, which could be a problem for you. You have also very simple model like all the linear models. All those linear models can be found in modeling least square regression linear model. You have linear, quadratic, and cubic equations, for example. You have constant, but constant means that you are going to have always the same value for all the time point. So what are the limitations? The limitations are, first of all, the number of samples that you have in vitro and or in the absorption. You have always to imagine something which is very simple. You need to have at least one sample more than the number of parameters that you want to estimate. Very simple to understand. If you have 2 sampling points, and you want to make a straight line with a slope and an intercept, your fit is going to be perfect, of course, but nonsense. To start to have an idea about the correctness of the fit, you need to have here a third point. So that means it's very important to understand that you need to have a number of parameters which is going to be equal to number of points plus minus one at least. That means you need at least to have one sampling more than the points. More you have samples, better is going to be the right fit. You need also to have criteria to compare the models and to have a plateau if you want to be sure to have the right F infinity. And then what is quite important to understand is that you could use that later for the time scaling. So to fit it, how you are going to do? In the fit, for example, for here the variable, you are going to select the equation that you want, and then you are going to run it. But one or two things which are quite important is the fact for a dissolution, and you can see that this dissolution reach here 100%, you may pay attention to what is going to be the fit of the F infinity. Because sometimes to have the best fit is going to imagine that you can continue to dissolve. And in this case, and that is the case here, you can see that he put a F infinity to 269% dissolved to have something which is good. So what could be, in this case, the maximum value of F infinity? You are going to tell me very easily that it's 100% for a dissolution. And I will tell you, no, it can be 105. Why? Because you know that the assay content can be, for example, plus minus 5% of a label. That means if you have in a tablet 105% of a drug, and you express it as a percent of a label, your dissolution curve can finish at 105. You can normalize it, of course, to the same quantity, but that is something else. So how can you set up, in this case, this F infinity to a fixed value? That is in the parameters that you have here in the parameter options that you can see on the bottom of this slide here. You have, you can see the screen, model selections, weighing factors, and parameter options. In the parameter options, you can, for example, fix the F infinity, you can see it, to 100% and not to let the system estimating it. In this case, it's going to be fixed. You can also add a weighing factor. This weighing factor can help you to have a best fit on the lower values. We are going to see some example. Have a look here. That is always the same equations. I have my formulation here. You can see that I have something which is increasing and then reaching a plateau. What I have done, 2 or 3 things. First of all, I have cut here the value after the maximum. Then I have tried to see if I let or not the system making what it wants. So when I put everything like this with a plateau, you can see that I have a fit which is not perfect on the top. Why? Because it's going to try to reach the last point. And if I enlarge it here, you can see that it's going to reach something which is 116%, not so bad. But you can see also that the fit at the beginning is not perfect. When I stop at 100%, it seems that I have a very nice fit of all my data, but my F infinity is going to go to 1,266%, which is not possible. So that means that starts to be a problem. When I use a quadratic equations, you can see that my fit is as good as the previous one. So which one I have to use? That is a good question. How can I know the best one? I can do it because I have a diagnostic panel in the modeling. In this diagnostic panel, I have a lot of criteria to help me to decide what is going to be the good fit. I can use either something like an Akaike criteria, or I can use a chi-square or F-test, which is going to be based, in this case, on the sum of square, residual sum of square, weighted or unweighted, the degree of freedom, and my number of parameters. So you can see I have a lot of tools that I can use here. But I have also to see the equations. If I want to modelize a dissolution and my F infinity, that means the quantity dissolved at the infinity, or the quantity absorbed, if I want to modelize my in vivo absorption curve, is greater than 100%, I must have a huge warning here. So something which is quite important, and explain you that the number of points could be of importance. I have here, in addition to 0, 0, 3 cases. The 3 cases are on the left here, A, C, and E. Those 3 cases correspond for A to 9 points, C to 5 points, and E to 3 points only. And I make exactly the same fit. What I can see, when I reduce my number of points, you can see that I have a problem. A and C, you can see that F infinity increase marginally, that MDT and B are almost similar, but when I reduce my number of points here only to 3, you can see that both parameters or all parameters, that means F infinity, MDT, and B, are not at all the correct one. That shows the importance in this case of the number of points in the right modelization. Something also which is quite important is to see if I have to use a simple or a double variable. That means if I have to complexify or not my equation. I have here a very nice sigmoid. I use a simple variable and a double variable. On the first look that you have here, and that is the raw data that you have on the top here and the result of the simulation and adjustment that you have in the bottom here, you can see that the first look that we have is that the adjustment seems to be perfect. This adjustment seems to be perfect, at least for all the points which are greater than 4 hours. Now, if we go in detail in the initial time points, you can see that if I have a single variable, my initial time points are not fit correctly here. And that if I have a double variable, I have a perfect fit. That is translated, for example, by my sum of square and also by the Aki-Ike criteria. Something which is quite important to see is that anyway, even with a double fit, my F infinity are still correct with almost 102%, that means 100% dissolved. That means in this case, the fact to add here a second term of the variable equations is going to provide the best fit for the initial values. Something that you could have tried is to use a single variable, but a weighing factor. So how to analyze the in vivo data and the importance of the right model? That is something which was published by Ivan Atomic in 2018, and that was a part of her work during her PhD thesis. You will find the full reference in the last slide. That is something also that we can do, because up to now we have only discussed about how to modelize dissolution curve. But you can make exactly the same thing for absorption curve. And that is very important to understand it. That is in vivo that we had. It was a very long-acting formulations over 1,500 hours. That means almost 3 months if you prefer. And you have here 2 peaks. That means a certain burst and then a second peak. And you had the in vivo input, which was here, the dotted line. What can you do? You can try in this case to see if you can modelize it and then use it later on to predict everything. So you have a lot of parameters. You have the AUC up to the time 48 hours. You have the AUC last, the AUC infinity, and the Cmax and Tmax values. Then you can have here the data and you have this absorption curve. Based on the absorption curve, you can try to make a double variable to try to modelize it. You can see that in this case, you have a very good model of a burst, a good model of a first peak, and you can see it on the prediction errors that you have here on the AUCs 0 to 48 and 0 to last, which is below 10%, but not so bad. The Cmax are good, but the AUC infinity is not good. That is due to the last part here. Then what you can try to do is to use a triple variable. You know that in a triple variable, the F1 plus F2 plus F3 is going to be equal to 100%, of course. And you can see that in this case, the fit is going to be perfect. Why? Because the last term of the Weibull equation is going to help you to predict the last part of your curve. You can do later on something which is quite interesting, is to try to modelize this absorption curve and to try to understand the mechanisms approach of each phases of the release. And in this case, and you will find that in the papers, and I'm not going to go in detail here, you will find what it is and what were, in this case, the different phases. That is based on the equation of Pepas, which was described in 1985, and all the analysis was made by Ivan Atomic. So that is quite interesting to see that you can use it in this case, and that if you use it, you can later on use these modelizations either to set up a good dissolution test and or to use it later on to predict everything. Another example of applications that I am going to give you here. It's how you can, for very long-acting injectable drug, try to see if you have the same functions to make the time scaling. That means either you can use an inverse release function or you can use something else. For example, this is something that we had in animal study, and that was in dogs for implants. Over here, you can see almost 1 year. You have again here a peak and a second release, that is the burst. Something which is very important when you start to analyze it and you want to analyze the absorption curve, which is what you have here. It's the first part which is here, is going to correspond to your burst, and this burst is going to correspond to less than 3 to 5% of the AUC. So that means the burst seems to be very important because you have a huge peak, but at the end that corresponds only to a very small quantity. Imagine that your dissolution is over 9 days and that in vivo you have almost 380 days. If you have a time scaling between the two, you will have something which, if it's a stretching, that means something like this, which is going to be a factor 42. But sometimes that is not the right one. Why? Because somehow it's something which you cannot stretch like this because the various phases are not going to take the same importance in vitro compared to the in vivo. Either you can use something like the inverse of a release function approach, which was described in 2019. But another approach is to try to make the modelization of your dissolution and absorption using the same type of equation, either the exponential, Weibull, Hill, or something like this. But what is something which is important is to have something which can help you to modelize both dissolution and absorption curve. For example, here, we have our in vivo data. We have all the here time concentrations and AUC. We have discussed about the problem of the initial burst. We have discussed also later on about the flip-flop, which could be very important if you use a Wagner-Nelson. So that means when we have the absorption curve, you can try then to make a model. And that is something that you can do. You can, for example, model it with here nothing more than a double Weibull. That means you have here the slope, you have here the time, and then you have a proportion that correspond to your burst, very small quantity, and that correspond to the slow release part. But now that you have something like this, that means that you have a model for the absorption. The only thing that you have to do if you want to go a little bit further is to try to see if you can use the same model to try to modelize your in vitro dissolution. That means you are going in this case to make the same fit, but you are going then to fix in vitro the burst here to the same, the beta, excuse me, to the same quantities, the F to the same quantities, and you will see in this case if the system can adjust the MDT. If yes, you have directly the IVIVC. And the way to develop this type of dissolution were described also by Atomic in 2016 in the way to try to develop an accelerated dissolution time for implants. So what do you have in this case? If in vivo and in vitro you have the same beta and you have the same F, but the MDT were changed, your time scaling is going to be nothing more than the direct ratio between the two MDTs. So that is something which is quite interesting. You can see in this case that the time scaling that you have for the burst is totally different than the time scaling that you have for the slow release part. So that is nothing more than an MDT based on the time scaling. This approach is very interesting because you can use it directly in a deconvolution by convolution approach. That means you can use it also when you want to make a convolution. So you can also use a very similar approach when you want to fix dissolution limits. So what is the interest in this case of Phoenix is that you can trace all the calculation, but you enter only once the time concentration, but you can secure all the process. And also you can have a lot of calculations. It's offer a lot of flexibilities. But of course, like in all the programs, you must use the right equation. This is all the references that we have here and that I cited in this webinar. The two last ones are the two examples that are the base of the example which are presented, and mainly the first one about the modelization of the in vivo. So I thank you, and if you have any questions, I have 5 minutes left, I think, on my time, even if I go a little bit more.
If you have any questions, if you wouldn't mind putting them in the chat.
Okay.
And I'm not seeing anything coming up now. So thank you, Dr. Cardot. We really enjoyed your presentation.
Okay.
I'd like to thank everyone else for joining us today. Our next webinar is scheduled for the 16th of August. The topic for that is pregnant women often have to take medication during their pregnancies. It's important to understand how pregnancy can alter the drug's pharmacokinetics. Duke University's Dr. Stephen Belvick will speak on leveraging an opportunistic study design to model PK in pregnancies complicated by systematic lupus. We hope that you have a great summer, and we look forward to you joining us again in August.
Thank you. Goodbye.